Picture this: you're floating in the vast emptiness of space, just beyond the crushing pull of a black hole. Your fellow astronauts inside the ship are moving at a normal pace, but for you, time has slowed to a crawl. Every second stretches into minutes, every minute into hours. A single heartbeat from your crewmates feels like an eternity to you. This isn't science fiction, it's the mind-bending reality of temporal anomalies, where time itself warps and twists under the influence of cosmic forces we're only beginning to understand. These aren't just quirks of the universe, they're windows into the deepest mysteries of space, time, and the very fabric of reality. Temporal anomalies, those unexplained distortions in the flow of time, aren't just theoretical curiosities. They've been observed, measured, and even predicted by some of the greatest minds in astrophysics. Einstein's theory of relativity showed us that time isn't the constant, unchanging force we once thought. Near massive objects like black holes or at speeds approaching light, time bends. It stretches, it behaves in ways that defy our everyday experience. But what happens when these distortions occur without clear cause? When time seems to stutter, skip, or even reverse in places where our current understanding says it shouldn't? That's where the real mystery begins. This journey isn't just about the science, it's about the profound implications these anomalies could have for our future. Imagine harnessing these distortions to travel through time, to explore distant galaxies without aging, or even to unlock secrets of the universe that have been hidden in plain sight. Or consider the eerie possibility that some of these anomalies aren't natural at all, that they could be signs of something or someone manipulating time itself. Today, we're diving deep into the most compelling cases of unexplained time distortions in space, from astronaut accounts to cutting-edge research that blurs the line between reality and the unimaginable. Strap in, because what you're about to discover will change how you see time forever. The fabric of the universe is far more flexible than we once believed, and nowhere is this more obvious than in Einstein's theory of relativity. Imagine spacetime as a stretched-out rubber sheet. When you place a heavy object like a planet or a star on that sheet, it creates a dent, warping the space and time around it. The stronger the gravity, the deeper the dent, and the more extreme the distortion. This isn't just poetic imagery, it's the foundation of how our universe actually works. Near massive objects like black holes, where gravity is unimaginably intense, time doesn't just slow down, it bends, twists, and behaves in ways that feel almost magical. Take something as ordinary as your phone's GPS. Those satellites orbiting Earth are actually experiencing time slightly faster than we are down here on the surface. Why? Because they're farther from Earth's gravity well, where space-time is less warped. If engineers didn't account for this difference, adjusting the satellite clocks by tiny fractions of a second, your navigation would be off by miles within minutes. That's the everyday proof of time dilation, a direct result of relativity in action. But gravity isn't the only force that can stretch time. Speed does it too. The faster you travel, the more time slows down for you compared to someone standing still. Picture twin astronauts. One stays on Earth while the other rockets through space at near light speed. When the traveling twin returns, they'd be younger than their Earth-bound sibling, a phenomenon called the twin paradox. It sounds like science fiction, but it's been confirmed with ultra-precise atomic clocks on fast-moving jets and even the International Space Station. Then there's gravitational lensing, another eerie effect of warped spacetime. When light from a distant star passes near a massive object like a galaxy, the gravity bends the light's path, creating distorted or multiple images of the same star, like a cosmic funhouse mirror. This isn't just a cool visual trick, it's how astronomers map dark matter and peer into regions of space we can't otherwise see. These phenomena aren't quirks, they're clues. Every time dilation measurement, every warped starlight observation is a piece of the puzzle, hinting at deeper layers of reality we've yet to uncover. And if gravity and speed can twist time like this, what else might be possible? Black holes aren't just cosmic vacuum cleaners, they're nature's ultimate time machines, bending reality in ways that challenge everything we think we know. Picture the iconic scene from Interstellar, where Matthew McConaughey's character watches years pass in minutes as he orbits the black hole Gargantua. While Hollywood took creative liberties, the science behind it is shockingly real. Near a black hole's event horizon, the point of no return, time doesn't just slow down. From an outsider's perspective, it appears to stop entirely. A clock falling toward the horizon would tick slower and slower until it seems frozen, its light stretched into an infinite redshift. Yet for the person falling in, time feels normal. They'd cross the horizon in what feels like moments, oblivious to the fact that the universe outside is racing forward without them. This isn't just theoretical. Astronomers have observed stars orbiting supermassive black holes, their light warped and slowed as they skim the edges of these gravitational monsters. The closer they get, the more their signals stretch, like a record playing at the wrong speed. But here's the paradox: if time stops at the horizon from an outside view, how can anything ever actually fall in? The answer lies in relativity's slippery nature. To the falling observer, the horizon isn't some dramatic barrier, it's just another point in space. The universe's rules don't break, they twist, revealing layers of reality where cause and effect aren't as straightforward as we'd like. And then there's the spaghettification effect, a gruesome but real consequence of tidal forces near a black hole. As you fall, gravity's pull on your feet is stronger than on your head, stretching you into a noodle of atoms. But even here, time plays tricks. From your perspective, the process might feel instantaneous, while someone watching from a safe distance would see you stretch and fade over millennia. These aren't just mind games. Researchers are using black holes as cosmic laboratories, testing the limits of physics. Some theories suggest that what happens inside a black hole might rewrite our understanding of time itself. That beyond the horizon, time could become space-like, turning the singularity into a moment in your future as unavoidable as tomorrow. Others speculate about wormholes, hidden tunnels through spacetime that could, in theory, connect distant points or even different times. The eerie takeaway: black holes don't just distort time, they expose how flimsy our everyday experience of it really is. In their shadow, the universe reveals its true, chaotic face, where the rules we cling to are just approximations and reality is far stranger than fiction. Imagine threads thinner than an atom stretching across the entire universe, cosmic strings, theoretical relics from the earliest moments of creation. These bizarre filaments, predicted by some models of the Big Bang, would carry unimaginable density, packing more mass than a mountain into a strand thinner than a proton. If they exist, their gravitational pull wouldn't just warp space, it would twist the very fabric of time around them like a tangled ribbon, potentially creating pathways to the past. Here's where it gets wild. If two cosmic strings moved past each other at near light speed, the spacetime between them could fold into something called a closed timelike curve, a loop where time circles back on itself. Step into this curve and you might find yourself traveling toward your own past, watching events unfold in reverse like a film reel spinning backward. Nobel Prize-winning physicist Kip Thorne once calculated that such a setup could, in theory, function as a time machine. There's just one catch: you'd need infinite energy to stabilize it, and the strings themselves might snap under the strain, collapsing the loop into a knot of cosmic chaos. But why do scientists take this seriously? Because cosmic strings aren't pure fantasy. They're a natural consequence of certain unified field theories, the same math that predicts black holes and gravitational waves. Some researchers even hunt for their fingerprints in the cosmic microwave background, the afterglow of the Big Bang, where tiny temperature fluctuations might reveal strings slicing through the infant universe. Others speculate that colliding strings could produce bursts of gravitational waves detectable by observatories like LIGO, ripples in spacetime signaling a crack in time itself. The implications are staggering. A civilization advanced enough to manipulate cosmic strings could stitch together timelines, revisiting historical moments or correcting cosmic accidents. But with that power comes paradox. What stops a traveler from altering the past in ways that erase their own future? Quantum mechanics might hold the answer, with theories like the self-consistency principle, suggesting the universe would conspire to prevent contradictions, forcing events to unfold in a way that preserves causality, even if it means bending reality to do so. Yet the most haunting possibility isn't technological, it's natural. If cosmic strings drift unseen through the cosmos, could some of history's unexplained anomalies, lost time episodes, déjà vu, even vanished civilizations, be caused by accidental brushes with these space-time faults? We don't know yet, but every time a physicist runs the numbers, the universe whispers back, time isn't the straight line we think it is. It's a maze, and cosmic strings might just be its hidden corridors. Wormholes, those mythical tunnels through space-time, aren't just the stuff of sci-fi. According to Einstein's equations, they could be real cosmic shortcuts, bending the fabric of reality to connect distant points in space or even different moments in time. Picture folding a sheet of paper so two dots touch, then punching a needle through. That's the essence of a wormhole. A traveler entering one end could emerge light years away, or perhaps centuries in the past or future, all in the blink of an eye. But here's the catch. These tunnels aren't just lying around waiting to be discovered. They'd require something bizarre to stay open: exotic matter with negative energy, a substance that defies gravity by pushing spacetime apart instead of pulling it together. Where would such a strange material come from? Surprisingly, the answer might lie in the chaotic quantum foam theorized to bubble beneath the fabric of reality. At unimaginably small scales, space isn't smooth. It's a seething sea of virtual particles popping in and out of existence. Among these fleeting fluctuations, tiny wormholes could spontaneously form and vanish in fractions of a second. Some physicists speculate that with enough energy and precision, we might one day stabilize these microscopic gateways, stretching them into usable tunnels. The Casimir effect, a real quantum phenomenon where two metal plates placed extremely close together in a vacuum experience an attractive force due to suppressed particle fluctuations, hints at how negative energy might be harnessed. It's as if the universe itself provides the blueprint for bending spacetime to our will, but the hurdles are staggering. Even if we could create or find a wormhole, keeping it stable would demand energies rivaling those of collapsing stars. One miscalculation and the tunnel could collapse into a singularity or sever its connection mid-journey, leaving travelers lost in the void. Then there's the paradox problem. If you step through a wormhole into the past and alter events, could you erase your own existence? Some theories suggest quantum mechanics might enforce a cosmic censorship, tweaking probabilities to prevent contradictions, while others propose parallel timelines branching off with every change. The tantalizing takeaway: wormholes remind us that time might not be the rigid, one-way street we perceive. If nature allows these shortcuts to exist, even in theory, then the universe is far more malleable and far stranger than we ever imagined. And somewhere in that quantum chaos, the keys to unlocking time itself might be hiding in plain sight. Quantum entanglement is one of the most bizarre and potentially universe-altering phenomena in physics. Imagine two particles born from the same event, separated by millions of miles, yet still mysteriously linked. Change the state of one, and its twin instantaneously mirrors that change, as if information is traveling faster than light. Einstein famously called this spooky action at a distance because it seemed to violate the cosmic speed limit he himself established. But what if entanglement isn't just about space? What if it's also twisting the very rules of time? Take the 2019 quantum delayed choice experiment, where scientists entangled photons across time, not just space. They manipulated one photon in the present, and its entangled partner, measured earlier, still responded as if the future had already altered the past. It's as if causality itself got tangled, with effects seemingly reaching backward through time. Then there's the quantum eraser experiment, where erasing information about a particle's path after it's been detected changes how it behaved in the past, like a cosmic undo button rewriting history. These aren't glitches, they're glimpses into a realm where time might not flow in one direction at all. The implications are staggering. If entangled particles can defy our linear understanding of cause and effect, could larger objects, even people, theoretically become entangled across time? Some interpretations of quantum mechanics suggest that every possible outcome of an event exists simultaneously until observed, branching into parallel timelines. In this many worlds view, time might be less like a river and more like a web, with entanglement stitching together moments that shouldn't logically connect. Then there's the tantalizing possibility that these quantum oddities could explain some of the temporal anomalies we've already discussed. Could sudden time skips or déjà vu be fleeting brushes with entangled states? When astronauts report distorted time perception in orbit, might they be sensing quantum links stretched across spacetime? The math hints at yes, but the truth is we're only beginning to grasp how deeply quantum mechanics and time might be intertwined. This isn't just theory. Labs worldwide are now testing these ideas with increasingly precise instruments, from superconducting qubits to atom interferometers. Every experiment pushes the boundaries of what we thought possible, revealing a universe far stranger and far more interconnected than we ever imagined. The more we probe these quantum mysteries, the clearer it becomes. Time may not be the steady, dependable constant we've always relied on. It might be something far more fluid, something we're only just learning to measure, let alone understand. Pulsars are often called the universe's most precise clocks, spinning neutron stars so regular in their rotations that their rhythmic pulses rival the accuracy of atomic timekeeping. These ultra-dense stellar remnants, no larger than a city yet massing more than our sun, whip around hundreds of times per second, beaming radiation like cosmic lighthouses with metronomic consistency. Astronomers use them as celestial GPS, mapping spacetime by their ticks, but sometimes these perfect clocks go haywire. Without warning, a pulsar's spin stutters, speeding up or slowing down in what scientists call a glitch. And these aren't minor hiccups. A single glitch can shave off or add milliseconds to a pulsar's rotation, as if an invisible hand grabbed the universe's stopwatch and twisted it. Take the 2006 case of PSRJ 1846-0258, a young, highly magnetized pulsar in the constellation Aquila. For years, it spun like a flawless timepiece. Then, in less than a day, its rotation rate jumped by a staggering 1 part in a million. That might sound small, but for an object weighing a quadrillion tons, it's the equivalent of a freight train suddenly lurching forward without any engine. The energy released in that split-second glitch was enough to power Earth's entire electrical grid for decades. So what could possibly cause such a violent shift? The leading theory points to the pulsar's interior, a superfluid soup of neutrons swirling beneath a crust harder than diamond. As the star spins, this crust slows slightly due to magnetic drag, while the superfluid underneath keeps racing ahead. When the strain becomes too much, the superfluid catches up in a sudden transfer of momentum, like a reconnecting gear jolting the system. But here's the mystery: some glitches don't fit this model at all. They're too large, too sudden, or happen in pulsars that shouldn't have enough internal friction to trigger them. That's where spacetime itself might come into play. Some astrophysicists speculate that certain glitches could be signatures of gravitational waves rippling through the pulsar, or even interactions with dark matter particles smashing into its core. Others wonder if these anomalies are glimpses of quantum gravity, effects, tiny fractures in spacetime structure only visible in the extreme gravity of a neutron star. Then there's the eerie possibility raised by the 2017 glitch of pulsar J083545, a pulsar that slowed down before speeding up as if something outside it, something we can't see, briefly tugged on the fabric of reality. Pulsar glitches remind us that even the universe's most reliable phenomena hide secrets. Every unexplained speed shift is a clue, a crack in the cosmic clockwork begging us to look deeper. And somewhere in that chaos, the answers to time's greatest mysteries might be ticking away, waiting for us to listen. In the vast emptiness between planets, two spacecraft drifted toward the stars, Pioneer 10 and 11, humanity's first emissaries to the outer solar system. Launched in the early 1970s, these robotic explorers were triumphs of engineering, venturing farther than any human-made object before them. But as they sailed into the void, something strange happened. Their trajectories began to deviate ever so slightly from predictions, as if an invisible hand were tugging them backward. By the 1980s, scientists realized both pioneers were experiencing an unaccountable deceleration, a tiny but persistent drift toward the sun, later dubbed the Pioneer Anomaly. At first, researchers dismissed it as a technical glitch, perhaps residual fuel leaking from the probes or uneven heat radiation throwing off their course. But when engineers crunched the numbers, none of these explanations fit. The deceleration was too consistent, too precise, an acceleration of roughly 9 trillionths of a meter per second squared, acting like a phantom drag no one could trace. Even stranger, later missions like Voyager and New Horizons didn't experience the same effect. If it were some universal quirk of deep space, why would it only target the pioneers? This is where spacetime itself enters the mystery. Some theorists suggested the anomaly might hint at an undiscovered gravitational effect, a subtle curvature in spacetime not accounted for by Einstein's equations. Others wondered if it could be evidence of dark matter's gravitational pull, or even a sign that our understanding of inertia breaks down at extreme distances. The most tantalizing and controversial idea was that the pioneers had brushed against a microscopic flaw in spacetime's fabric, a kind of cosmic friction warping their path. Imagine sailing a boat across a calm lake, only to find patches where the water inexplicably thickens, slowing you down without ripple or reason. Then, in 2012, a team of researchers cracked part of the puzzle. After poring over decades of telemetry data, they realized the anomaly wasn't external at all, it was the spacecraft themselves. Heat radiating from the Pioneer's power systems was pushing back on them with just enough force to account for the drift. Case closed, not quite. While thermal radiation explained most of the effect, a tiny residual anomaly lingered, too small to dismiss outright. Was it noise in the data or something deeper? The Pioneer's legacy endures as a humbling reminder. Even in the era of precision physics, the universe still holds surprises. Their phantom deceleration may have been mostly solved, but that sliver of uncertainty keeps the door open. A whisper that somewhere in the darkness, spacetime might still be hiding wrinkles we've yet to smooth out. A journey to Proxima Centauri, the closest star to our Sun at just over 4 light-years away, should take roughly 4 years if you could travel at light speed. But here's the catch: no object with mass can ever reach that velocity. Even if we built a ship capable of 99% the speed of light, the trip would still take about 4 years and 2 months from Earth's perspective. Yet for the astronauts on board, time wouldn't just pass more slowly. It would warp in ways that defy intuition. Thanks to relativity, their clocks would tick at a fraction of the rate we experience here at home. A 4-year voyage for Earthbound observers might feel like mere months to the crew, aging them barely a fraction of what their families back home endure. Picture identical twins, one stays on Earth while the other boards this near light-speed ship. When the traveling twin returns after what feels like 8 months to them, they'd step out to find Earth has aged over 8 years. Their sibling would be grayer, older, while they'd barely have missed a season. This is the twin paradox in action, and it's not just a thought experiment. Atomic clocks flown on jets and satellites have confirmed it. Time slows down for moving observers, and the faster you go, the more extreme the effect becomes. Now scale this up. Imagine a ship accelerating continuously at one gravity comfortable enough to mimic Earth's pull toward Proxima Centauri. After roughly 3.5 years of ship time, the crew would reach 99% light speed, covering the distance in what feels like just under 4 years to them. But back home, over a decade would have passed. Push further, and the numbers get staggering. At 99.9% light speed, the trip shrinks to under 7 months for the crew, while Earth clocks tick off 6 years. The closer you get to light speed, the more time bends in your favor. But relativity doesn't just twist time, it warps space too. From the astronaut's perspective, the distance to Proxima Centauri wouldn't be 4 light years. It would contract, squeezed by their velocity, until the star appears just a fraction of its true distance away. This isn't an illusion, it's how spacetime itself responds to motion. The faster you fly, the more the universe ahead compresses, making destinations reachable in far less time than traditional math suggests. The implications are profound. A crew traveling at these speeds could reach stars tens of thousands of light years away within a human lifetime, though everyone they ever knew would be dust by the time they returned. Time dilation isn't just a quirk of physics, it's a one-way ticket, reshaping not just space travel but the very meaning of distance and time. The stars might be closer than they appear if you're willing to pay the ultimate price, leaving your own era behind. Dark matter doesn't just lurk unseen in the cosmos, it might be actively bending time itself. We've known for decades that galaxies rotate too fast for the visible matter they contain, their outer stars whipping around as if gripped by an invisible hand. That missing mass, the elusive dark matter, doesn't emit or reflect light, but its gravitational pull is undeniable. Now, imagine if that pull doesn't just tug on stars, it twists the very fabric of spacetime around it, creating localized pockets where time flows differently. These time bubbles could be scattered throughout the universe, hidden in plain sight. Take the Bullet Cluster, one of the most dramatic pieces of evidence for dark matter's existence. When two galaxy clusters collided, their visible gas slowed and heated up, but gravitational lensing revealed most of their mass, the dark matter, had sailed right through, barely interacting. If dark matter can pass through itself and regular matter like a ghost, what does that mean for spacetime in its wake? Some models suggest its uneven distribution could create subtle gradients in time's flow, like invisible whirlpools where clocks tick fractionally slower or faster. These wouldn't be dramatic time warps like near a black hole, more like faint ripples, detectable only with impossibly precise instruments. Then there's Galaxy NGC 1277, a spiral with such an extreme rotation curve that its outer stars move as if the galaxy's mass is concentrated in a tight, invisible sphere at its core. Traditional dark matter models struggle to explain this, but what if the answer lies in spacetime itself? If dark matter in that region warps time enough to affect orbital dynamics, it could create the illusion of extra mass where none exists. Think of it like a carousel spinning on a slope. The tilt changes how fast the horses move, even if the motor's power stays the same, the wildest possibility. These time bubbles might not be static. Dark matter isn't spread evenly, it clumps in filaments and halos, and some theories suggest it could even form exotic structures like topological defects, cosmic knots where spacetime tangles in on itself. Near these anomalies, time might stutter, loop, or even fracture momentarily. While we've never directly observed such effects, they could explain certain astronomical oddities, like quasars whose brightness fluctuates too rapidly to fit conventional physics, or cosmic rays with energies that defy known processes. Of course, proving any of this is a monumental challenge. Current atomic clocks aren't sensitive enough to detect the nanosecond scale discrepancies these bubbles would produce. But next-generation experiments like space-based quantum interferometers or pulsar timing arrays might get us close. If we could map the universe's gravitational field with enough precision, we might uncover spacetime's hidden wrinkles, places where dark matter's grip quietly reshapes time itself. Until then, these ideas remain at the edge of science, tantalizing, unproven, and utterly transformative if true. The universe's greatest secret might not just be what dark matter is, but what it's doing to time right under our noses. If black holes are the universe's ultimate sinks, swallowing everything that crosses their path, then white holes are their theoretical opposites, cosmic fountains firing matter and energy outward with relentless force. Imagine a black hole running in reverse. Instead of an event horizon that traps light forever, a white hole would have one that repels it, ejecting everything inside like an unstoppable geyser. These bizarre objects aren't just science fiction. They emerge straight from Einstein's equations as valid solutions to the laws of relativity. But while black holes are backed by overwhelming observational evidence, white holes remain purely hypothetical, lurking at the edge of known physics like ghosts of cosmic symmetry. The math behind them is eerily elegant. In theory, if you could film a black hole's formation and play the tape backward, you'd see a white hole, a burst of matter exploding into existence from a singularity. Some physicists speculate they could be the other end of black holes, connected via wormholes in a grand cosmic recycling system. Others propose an even wilder idea, that white holes might be how our universe began. The Big Bang itself, with its sudden eruption of energy from an infinitely dense point, bears striking resemblance to a white hole's behavior. Could our entire cosmos be the aftermath of a white hole's explosion? It's a tantalizing possibility, though one that's nearly impossible to test. Then there's the quantum angle. At microscopic scales, particles can briefly tunnel into existence from seemingly empty space, violating energy conservation for fleeting moments. Apply this principle to a collapsing star, and some theories suggest quantum effects might halt its collapse into a black hole, triggering a bounce, a reversal that transforms it into a white hole. These quantum-corrected black holes wouldn't last forever. After billions of years, they'd spontaneously burst open, releasing their trapped contents in a fiery rebirth. It's as if time itself hiccuped, flipping the rules of gravity inside out. But why haven't we seen one? If white holes exist, they'd be hard to miss, blazing with radiation as they disgorge entire stars' worth of matter. One explanation is that they're extraordinarily short-lived, collapsing almost instantly under their own gravitational pull. Another is that they're hidden behind event horizons just like black holes, making them indistinguishable from the outside. Or perhaps they're banished to the far future, waiting until the dying embers of the universe to awaken. The most intriguing clue might lie in fast radio bursts, those mysterious milliseconds-long pulses of energy from deep space. Some theorists suggest these could be white holes flickering into existence and vanishing just as quickly, their outbursts echoing across the cosmos like cosmic alarm clocks. Until we catch one in the act, though, white holes remain one of physics' most tantalizing what-ifs, a reminder that the universe's extremes might hold symmetries we're only beginning to imagine. In 2022, NASA ran an experiment so precise it could measure the slightest hiccup in time itself, and it all hinged on a pair of atomic clocks aboard the International Space Station. These weren't ordinary timekeepers, they were hydrogen maser clocks so accurate they'd lose less than a second over 10 million years. But here's the twist: after months in orbit, the clocks didn't quite match their Earth-bound counterparts. They ran ever so slightly faster, just a few fractions of a nanosecond per day, but enough to confirm one of Einstein's boldest predictions. Time, it turns out, really does pass differently when you're farther from Earth's gravity. This phenomenon, called gravitational time dilation, stems from relativity's core idea. The stronger the gravity you're in, the slower time flows. Earth's mass warps spacetime around it, creating a kind of gravitational well where clocks at sea level tick slower than those in space. The IS, orbiting 250 miles up, sits just high enough to escape the deepest part of that well. The difference is tiny, about 1 second lost every 3 years compared to Earth's surface, but measurable. NASA experiment wasn't just proving Einstein right. It was refining our ability to track these minuscule shifts with unprecedented precision. What makes this so groundbreaking? Atomic clocks in space aren't just scientific curiosities, they're the backbone of modern navigation. GPS satellites already account for time dilation, adjusting their clocks to stay synchronized with Earth. Without these corrections, your phone's map would drift off course by miles within minutes. But the ISS experiment pushed this further, using ultra-stable lasers to isolate the clocks from vibrations, temperature swings, and even the station's own motion. The result, a cleaner measurement of pure gravitational effects, free from the noise that muddies Earth-based tests. The implications stretch far beyond navigation. Imagine future missions to Mars, where the weaker gravity could mean colonists age microseconds faster than those on Earth. Or consider pulsar timing arrays, which rely on ultra-precise clocks to detect gravitational waves, the faint ripples from colliding black holes. The better we understand how gravity warps time, the sharper our cosmic vision becomes. But here's the lingering mystery. While the ISS data matched Einstein's predictions, some measurements at higher altitudes, like the gravity probe experiment in the 1970s, showed tiny discrepancies. Could there be unseen factors tweaking time's flow, dark matter, quantum foam? The answers might lie in next-generation clocks, like those planned for the Lunar Gateway, where the moon's weaker gravity will stretch time even further. Every tick of these celestial metronomes brings us closer to unlocking spacetime's deepest secrets, 1 nanosecond at a time. Time crystals sound like something ripped from a sci-fi novel, yet they're one of the most groundbreaking discoveries in modern physics, structures that pulse and repeat not in space but in time. Picture a clock that ticks forever without winding, or a snowflake that cycles through its shape endlessly without melting or refreezing. That's the eerie essence of a time crystal, a quantum arrangement of particles that oscillates in a perfectly stable loop, breaking the symmetry of time itself. Normally, if you leave a system undisturbed, say a pendulum at rest, it won't spontaneously start swinging. Energy has to be added, but time crystals defy this. Once kick-started, their atomic structure flips between states indefinitely, like a cosmic metronome that never winds down. The secret lies in quantum entanglement. Particles in a time crystal lock into a rhythm where their interactions create a self-sustaining dance, immune to entropy's usual decay. It's as if they've found a loophole in the universe's rulebook, where motion doesn't require continuous energy, just the right initial quantum nudge. The implications are staggering. Take quantum computing, where maintaining coherence, keeping qubits stable long enough to perform calculations, is the holy grail. Time crystals could act as flawless quantum memory, their unshakable rhythm preserving information against the noise that plagues traditional systems. Imagine a processor where data isn't stored in fragile electron spins, but in the immutable beats of a time crystal's pulse. Researchers at Google and Stanford have already built rudimentary versions using superconducting qubits, observing these bizarre structures pulse for minutes, an eternity in quantum terms. Yet the real magic lies in what time crystals reveal about reality. By breaking time symmetry, they challenge our most basic assumptions, that physical laws work the same forward and backward. A time crystal's oscillations are directionally stuck like a wheel that only turns clockwise, even if time reverses. This could rewrite how we understand everything from thermodynamics to the arrow of time. Some theorists even speculate that time crystals might be hiding in plain sight, embedded in exotic materials, or even lurking in the quantum foam of empty space. The hunt is now on to scale these structures beyond lab curiosities. If we can harness their perpetual rhythm, we might unlock technologies that seem like magic today, engines that run on correlated quantum fluctuations, or sensors so precise they detect the faintest ripples in spacetime. Time crystals aren't just a new state of matter, they're a glimpse into a deeper layer of physics, where time isn't a backdrop but a material we might one day shape. The Fermi paradox has haunted scientists for decades. If the universe is so vast and ancient, where is everyone? With billions of potentially habitable planets, why haven't we found a single trace of intelligent life? One chilling possibility is that we're not just alone, we've been deliberately isolated, and the reason might lie in the manipulation of time itself. Think of Earth as a nature reserve in a galactic zoo. The so-called zoo theory suggests advanced civilizations could be observing us from a distance, enforcing a cosmic quarantine to let humanity develop undisturbed. But how would they stay hidden for millennia without leaving any detectable footprint? The answer might involve temporal engineering. If an alien society could control time with precision, they could cloak their presence by placing observational outposts in carefully constructed time bubbles, regions where time flows at a different rate than the surrounding universe. From our perspective, their monitoring stations might only flicker into existence for microseconds every century, far too brief for our telescopes to catch. Even more unsettling is the idea of a temporal quarantine. Imagine a civilization so advanced that they've learned to manipulate causality, enforcing strict rules about contact with younger species to prevent paradoxes or cultural contamination. Just as we protect uncontacted tribes on Earth to preserve their autonomy, these aliens might use time dilation fields to create an impassable barrier around our solar system, not in space but in time. A ship attempting to approach Earth at relativistic speeds could find itself trapped in a loop, arriving back at its starting point the moment it crosses an invisible threshold. The absence of alien megastructures or radio signals might not mean they don't exist. It could mean they've mastered chrono-avoidance, hiding in temporal folds we don't yet know how to measure. Some researchers speculate that certain dark matter anomalies or gravitational lensing glitches could be signatures of these hidden time enclaves. Others point to fleeting astronomical phenomena like vanishing stars or inexplicably delayed cosmic rays as potential evidence of civilizations tinkering with spacetime's fabric. If this sounds like science fiction, consider humanity's own trajectory. We're already experimenting with quantum systems that hint at time's malleability. What might a species thousands or millions of years ahead of us achieve? The silence of the cosmos might not be silence at all. It could be the quiet hum of a universe where time isn't just a dimension but a tool, wielded by minds we can't yet comprehend. Ancient civilizations left us puzzling tales of gods descending from the skies, beings who appeared in flashes of light, wielded impossible knowledge, and vanished without warning. The Mayans spoke of Kukulkan, the feathered serpent who brought wisdom before ascending back to the heavens. Hindu texts describe Vimanas, flying chariots that moved at the speed of thought. Even the Bible's Ezekiel witnessed a wheel within a wheel descending from the clouds. For centuries, these stories were dismissed as myth or metaphor. But what if these accounts weren't just imagination? What if they were distorted memories of real encounters with something beyond human understanding? Modern UFO reports echo these ancient legends with eerie precision. Witnesses describe craft that defy physics, sudden accelerations, right-angle turns, vanishing mid-air, all hallmarks of objects unbound by our rules of motion. Yet the strangest detail isn't their movement, it's their effect on time. Pilots report losing minutes or hours during close encounters. Radar systems show targets appearing in two places at once. One declassified Pentagon case documents a Navy crew experiencing missing time while tracking a UAP that danced erratically off the coast of San Diego, as if the object and everything near it briefly slipped into a different temporal frame. This isn't just coincidence. Both ancient myths and modern sightings share a common thread: distortions in perceived time. The Dogon tribe of Mali, who inexplicably knew of Sirius B, a star invisible to the naked eye, claimed their knowledge came from amphibious visitors who emerged from a spinning vortex. Greek legends tell of Apollo's chariot crossing the sky in an instant, while Norse sagas describe the Bifrost Bridge as a fleeting, shimmering path between worlds. Today, astrophysicists speculate that traversable wormholes or Alcubierre warp bubbles, theoretical constructs that bend spacetime, could produce exactly these effects: sudden appearances, impossible speeds, and localized time anomalies. The most chilling parallel lies in abduction accounts. Experiencers often describe being taken into crafts where time behaves unnaturally. Clocks stop, conversations last hours yet feel like minutes, or vice versa. Some recall floating through walls or seeing their own bodies from outside, as if spacetime itself had glitched. Neurologists argue these could be seizures or hallucinations, but what if they're glimpses of a technology that manipulates time like clay? Ancient texts hint at similar disorientation. The Sumerian king Etana, carried skyward by an eagle, describes the earth shrinking like a basket beneath him, a startlingly accurate depiction of relativistic time dilation centuries before Einstein. Perhaps the so-called gods were never divine at all. Maybe they were explorers from a civilization harnessing temporal physics we're only now beginning to grasp. Their miracles, instant healings, prophecies, vanishing acts might be side effects of technology that compresses or stretches time at will. The Akashic Records, a Hindu concept of a cosmic library containing all knowledge, sounds suspiciously like a quantum database where past, present, and future coexist. Even the biblical burning bush, which burned without being consumed, mirrors reports of UFOs hovering motionless for hours, an effect achievable if time within their field is slowed to near stasis. The implications rewrite history. Those ancient temples aligned with stars, they might not just be calendars. They could be landing beacons tuned to frequencies we no longer understand. The Great Pyramid shafts, perfectly angled toward Orion's belt, might have guided more than just pharaohs' souls, and those recurring myths of floods and fire from the sky. They could describe failed experiments in temporal engineering, catastrophic ruptures in spacetime that early humans interpreted as divine wrath. As we uncover more about quantum mechanics and relativity, the line between myth and science blurs. Those ancient sky gods, with their sudden appearances and reality-defying powers, might not have been supernatural. They could have been post-natural, wielding a physics so advanced it looked like magic. And if that's true, the next time a UAP flickers across the sky, we might not just be watching a visitor from across the stars, but from across time itself. Astronauts floating in the void of space have reported eerie moments where time itself seemed to slip, like veteran cosmonaut Sergei Krikalev, who orbited Earth for over 800 days across 6 missions. During one extended stay on Mir, he described a sudden, overwhelming sense of familiarity while gazing at the planet below, as if he'd lived that exact moment before. The stars outside the porthole, the hum of the life support systems, even the weightlessness, all of it felt replayed. Then came the strangest part. His mission log showed a blank stretch of nearly 20 minutes he couldn't account for, as if someone had pressed pause on his memory. This wasn't an isolated incident. Apollo 11's Michael Collins, orbiting the moon alone while Armstrong and Aldrin walked its surface, later wrote about a bizarre temporal distortion during the mission's quietest hour. With Earth and Moon both out of view, he felt suspended in a limbo outside time, where seconds stretched unbearably long, only to later discover his wristwatch had inexplicably gained 3 minutes. Meanwhile, high-altitude pilots like those testing the SR-71 Blackbird reported similar anomalies. During flights at Mach 3, Some described brief but vivid flashes of prescience, as if they'd already executed the next maneuver before their hands moved. One declassified CIA report even mentions a U-2 spy plane pilot who, after a stint at 90,000 feet, insisted his mission had lasted no more than an hour, despite flight logs confirming 4. Neurologists have theories. In extreme environments, the brain's internal clock, a network of neurons in the suprachiasmatic nucleus, can misfire. Low gravity alters fluid distribution in the inner ear, disrupting our sense of motion and duration. Cosmic radiation might even cause micro-glitches in temporal processing, like a computer skipping a frame. But these explanations hit a wall when faced with the consistency of the reports. Why do so many astronauts describe the same missing time episodes or déjà vu flashes, even on different missions? And why do these anomalies cluster around moments of profound isolation, like Collins's lunar solitude or Krikelev's midnight pass over the Pacific? The overlap with fighter pilots is especially telling. Both groups operate in high-stress, low-sensory environments where routine cues for timekeeping, like daylight cycles or ground movement, are absent. Yet pilots aren't exposed to the relativistic time dilation astronauts experience from orbital speeds. This suggests something else is at play. Perhaps extreme altitude and near-space conditions create pockets of altered perception where the brain defaults to a dreamlike state. Studies at NASA, a neutral buoyancy lab, show that prolonged weightlessness can rewire spatial awareness, making even simple tasks feel uncanny. Could time perception be just as malleable? Then there's the curious case of Scott Kelly's year on the ISS. After returning, his DNA showed unexpected changes, telomeres lengthening, gene expression shifting, as if his cells had reset their biological clocks. More haunting were his journals, where he documented recurring moments of time compression, watching sunrises flicker past every 90 minutes until days blurred into a surreal loop. It wasn't just fatigue, he later admitted. It was like living in a sped-up film reel, but with these gaps, like parts got cut out. The most provocative parallel lies in neurological research on time perception under stress. When the amygdala fires in life or death situations, the brain records memories in hyper-detail, creating the illusion of slowed time. Think car crashes feeling like slow motion. But what happens when stress is chronic, like weeks in orbit? Some researchers speculate the brain might compensate by editing time, stitching together only the most salient moments to avoid overload. That could explain the missing stretches astronauts report. Not lost time, but time the mind refused to process. Yet for all the rational theories, the accounts share an unsettling thread. These anomalies often coincide with heightened states of awe. Whether it's Collins seeing the moon's far side alone or Kelly watching 16 sunrises a day, the overwhelming vastness of space seems to trigger something deeper than neurology can explain. Ancient cultures believed such moments opened portals to the divine. Modern physics wonders if they're glimpses of spacetime's true fluidity. Whatever the answer, one thing's clear: when humans step beyond Earth, time doesn't just bend. It flickers. What if the time anomalies we've been exploring aren't cosmic accidents, but glitches in the code of reality itself? Simulation theory, the mind-bending idea that our universe might be an artificial construct, has gained traction in recent years, and not just among sci-fi fans. Tech mogul Elon Musk famously put the odds of us living in base reality at 1 in billions, suggesting it's far more likely we're digital beings in some advanced civilization simulation. And if that's true, then temporal distortions could be something far stranger than physics quirks. They might be the equivalent of software bugs in a vast cosmic program. Think about it. In any complex simulation, tiny errors inevitably creep in: floating point rounding glitches, latency hiccups, or memory leaks. Now imagine those same errors playing out on a universal scale. Pulsar glitches that defy conventional physics could be a processing delay in the celestial clock subroutine, the pioneer anomaly's phantom deceleration. Maybe a rounding error in the gravity calculation engine. Even quantum entanglement's spooky action at a distance starts to make eerie sense if you frame it as two variables sharing a pointer in an optimized simulation. No faster-than-light communication needed because the system simply updates both values simultaneously in the code. Some of the most puzzling time anomalies line up disturbingly well with this idea. Take the 2004 time tsunami reported by NASA Chandra X-ray Observatory, a bizarre gravitational wave that seemed to rewind a section of spacetime near a black hole as if someone had hit undo on a cosmic keyboard. Or consider the quantum-delayed choice experiments, where particles appear to retroactively change their behavior based on future measurements, like a program lazily rendering details only when the player looks at them. Even our everyday déjà vu could be explained as a brief cache mismatch, where the simulation accidentally loads a memory buffer twice, the wildest part. Physics itself might be hinting at this. At the smallest scales, spacetime isn't smooth, it's pixelated, with a fundamental Planck length below which measurements become meaningless. That's exactly what you'd expect if reality ran on discrete computational units. The holographic principle, derived from black hole physics, suggests all 3D information in a volume of space might be encoded on its 2D boundary, a cosmic compression algorithm to save processing power. Even the speed of light could function as a clock rate limit, preventing the simulation from overheating from too many calculations at once. But here's where it gets really meta. If we are in a simulation who's to say time flows linearly for the simulators, their reality might operate at a different time scale entirely. What feels like billions of years to us could be seconds in their frame of reference. Our universe's time glitches might just be background processes running on their hardware, or debug routines probing our sector of the simulation. Some theorists even speculate that conscious observation, the infamous measurement problem in quantum mechanics, is how the simulation conserves resources, only fully rendering reality when someone's looking. Of course, not everyone buys this digital metaphysics. Critics argue it's unfalsifiable, a clever metaphor that explains everything but predicts nothing. Yet the persistence of certain anomalies, from quantum non-locality to dark matter's ghostly influence, keeps the door open. After all, if you were designing a universe simulating AI, wouldn't you hide the artifacts in the places hardest to observe? The deeper we probe spacetime's fabric, the more it behaves like an elegant but imperfect piece of engineering. Maybe the ultimate temporal anomaly isn't a black hole or a cosmic string, but the growing suspicion that we're living in someone else's save file. Time loops have captivated audiences for decades, with films like Groundhog Day turning the concept into pop culture shorthand for reliving the same moment endlessly. But Hollywood's take on temporal recursion often glosses over the science, or leans into pure fantasy. Compare Bill Murray's inexplicably repeating day to Christopher Nolan's Tenet, where time inversion creates a far more complex, if convoluted, dance of cause and effect. In Tenet, objects and people move backward through time, their entropy reversed, leading to mind-bending scenes like bullets flying into guns instead of out of them. Nolan consulted physicists to ground the premise in real theoretical concepts, but even he admitted taking creative liberties. The result feels closer to speculative fiction than hard science, a thrilling puzzle box, but one that bends the rules as much as it follows them. Then there's Primer, the ultra-low-budget indie film that treats time loops like a math problem. Its engineers accidentally create a box that lets them relive 6-hour segments, leading to recursive paradoxes so dense viewers need flowcharts to untangle them. Unlike Groundhog Day's magical realism or Tenet's blockbuster spectacle, Primer digs into the gritty logistics. How do you avoid your past self? What happens if you alter events you've already experienced? The film's answer is bleak. Every loop fractures reality further, with characters branching into alternate timelines where trust erodes and identities splinter. It's a hauntingly plausible take on how humans might actually misuse time loops, not for self-improvement but for control, paranoia, and self-destruction. These stories tap into a real scientific debate. Closed timelike curves, theoretical pathways where time bends back on itself, are mathematically possible in Einstein's relativity under extreme conditions, like near a rotating black hole or cosmic string. But Stephen Hawking argued nature likely forbids them via his chronology protection conjecture. Quantum effects would create destructive feedback, a surge of infinite energy, the moment someone tried to engineer a time loop, effectively slamming the door on paradoxes before they happen. It's as if the universe has a built-in fail-safe against time travelers, a cosmic no to cheating causality. Yet some physicists disagree. Nobel laureate Kip Thorne's work on wormholes suggests delicate loops might avoid self-annihilation if exotic matter stabilizes them. Others propose quantum entanglement could thread the needle, allowing information to loop without collapsing into chaos. The truth is, we don't know yet. Time loops sit at the edge of known physics, where equations and imagination collide. Pop culture gives us the drama and dread of reliving moments, but science hints that if loops exist at all, they'd be far stranger, rarer, and more dangerous than any movie has dared to show. Einstein's equations have always been a playground for mind-bending possibilities, but few solutions are as strange or as haunting as Kurt Gödel's rotating universe. In 1949, the legendary mathematician and logician, best known for shattering the foundations of mathematics with his incompleteness theorems, turned his genius to cosmology. What he discovered was a universe where time wasn't just relative, it was optional. Gödel's solution described a cosmos spinning as a whole, where the sheer rotation twisted spacetime into closed time-like curves, loops that could carry you back to your own past. No black holes, no wormholes, just the sheer momentum of the universe itself bending time into a circle. The mechanics are dizzying. In Gödel's model, the entire cosmos rotates like a vast, invisible carousel, dragging space-time along with it. If you traveled far enough in a straight line, you'd eventually return to your starting point, not just in space, but in time. It's as if the universe were a giant Möbius strip where forward motion becomes backward motion without you ever changing direction. Gödel himself relished the paradoxes this created, pointing out that in such a universe you could attend your own birth or witness the dawn of history firsthand. But here's the puzzle. If Gödel's rotating universe is mathematically valid, why don't we see evidence of it? Observations show our cosmos is expanding, not spinning uniformly. There's no cosmic whirlpool tugging at galaxies, no great spiral of time winding backward. Or is there? Some physicists speculate that rotation might still lurk in subtler forms. Dark flow, the mysterious tendency of galaxy clusters to stream toward a single point in space, could hint at residual spin from the early universe. Others suggest that local regions, like the vicinity of rotating black holes, might mimic Gödel's conditions on smaller scales, creating pockets where time loops briefly stitch together. The most intriguing twist, Gödel's universe doesn't just allow time travel, it demands it, as a feature baked into the geometry of reality. Unlike wormholes or cosmic strings, which require exotic matter or infinite energy to stabilize, Gödel's closed time-like curves emerge naturally from the equations. No engineering, no futuristic technology, just the raw physics of a spinning cosmos. That's what makes it so unsettling. If his solution is even partially true, time loops might not be rare anomalies. They could be hiding in plain sight, woven into the fabric of everything, waiting for us to stumble into them. Of course, Gödel's model isn't the final word. Modern cosmology, with its emphasis on dark energy and inflationary expansion, paints a very different picture of the universe, but the fact that Einstein's equations permit such a reality raises deeper questions. Are we missing something fundamental about the cosmos, or is nature simply more inventive and more paradoxical than we've dared to imagine? Gödel's rotating universe remains a tantalizing footnote in physics, a reminder that even our best theories might be sketches of a far weirder truth. And somewhere in that spinning void, the past might not be as distant as we think. Tachyons are one of physics' most tantalizing what-ifs, hypothetical particles that don't just break the speed limit of light but shatter it entirely, moving faster from the moment they're born. Unlike ordinary matter, which can only approach light speed asymptotically as energy increases, tachyons would start their existence already faster than light, slowing down as they lose energy. But here's the twist that bends reality. If such particles exist, they wouldn't just defy Einstein's cosmic speed limit, they'd effectively move backward in time. The math behind this is eerie yet elegant. Special relativity treats faster than light travel as a mirror world where time and space flip roles. Just as slowing below light speed locks us into a forward-moving timeline, tachyons, always superluminal, would experience time in reverse from our perspective. A tachyon emitted from a lab experiment might arrive at its destination before it was even created, its detection appearing to precede its origin. It's as if causality itself unravels in their wake, with effects preceding causes in a dizzying inversion of reality. This isn't just theoretical noodling. In 1967, physicist Gerald Feinberg coined the term tachyon from the Greek tachys, meaning swift, and showed these particles could fit within relativity's equations without outright contradictions, so long as they could never slow down to light speed. But the real shock came in 2011, when CERN Opera experiment detected neutrinos apparently arriving 60 nanoseconds faster than light should allow. For a brief, electrifying moment, it seemed tachyons might be real. Headlines screamed about time travel. Physicists scrambled to replicate the results. Then came the letdown. A loose fiber optic cable and a misaligned atomic clock were to blame. The neutrinos had obeyed Einstein after all, yet the tantalizing possibility lingers. Quantum field theory allows for tachyon-like fields not as particles but as instability triggers. Some theories of the early universe suggest a tachyon condensation phase might have powered cosmic inflation, flipping the script so these speedsters helped stabilize reality rather than unravel it. String theory, too, flirted with tachyons as artifacts of unstable vacuum states before researchers found ways to lift them out of the equations. Even modern experiments hunt for tachyon-like effects in exotic materials, where quasi-particles can mimic superluminal behavior without breaking causality. The most haunting implication: if tachyons exist, they might not just move through time, they could carry it. Some models suggest a tachyon field could permeate space, its vibrations defining the arrow of time itself. In this view, our forward-marching experience of cause and effect might be a collective illusion, a statistical fluke in a universe where time's flow is fundamentally reversible. It's a reminder that physics' deepest mysteries often lurk in the gaps, not just between what we know and don't know, but between what we've dared to imagine and what the universe has quietly already allowed. The cosmic microwave background, the faint glow left over from the Big Bang, should be the ultimate snapshot of a smooth, uniform infant universe. But when scientists mapped its subtle temperature variations with satellites like WMAP and Planck, they stumbled on something unsettling. The data revealed peculiar asymmetries, regions where hot and cold spots align in ways that defy standard cosmology, the most notorious of these anomalies. The so-called axis of evil, a bizarre alignment of fluctuations stretching across the cosmos like a cosmic scar, pointing in a direction that seems to break the fundamental rule that the universe should look the same in all directions. At first glance, the name sounds like hyperbole, but the implications are anything but trivial. According to the Standard Model, quantum fluctuations in the early universe should have created a random, isotropic pattern, like static on an old TV screen. Instead, the CMB shows large-scale correlations along this mysterious axis, with one hemisphere slightly warmer than the other. It's as if the universe has a preferred orientation, a cosmic tilt that challenges the bedrock principle of cosmological homogeneity. Some researchers dismiss it as a statistical fluke or an artifact of foreground interference, like dust in our own galaxy. But the odds of such an alignment occurring by chance are less than 1 in 1,000, enough to keep physicists awake at night. One radical explanation: these anomalies could be fingerprints of something far older than the Big Bang. Theories like conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose, suggest our universe might be just one in an endless cycle of expansions and contractions. If true, the CMB's odd patterns could be echoes of collisions between black holes from a previous cosmic epoch, ghostly imprints lingering in the fabric of spacetime. Others speculate they're evidence of a defect in the early universe, like a cosmic string or domain wall left over from a phase transition in the first moments after creation. Picture freezing water cracking as it expands, except the cracks are fractures in spacetime itself, etched into the CMB for eternity. Then there's the cold spot, another CMB anomaly that refuses to fit the mold. This region, spanning nearly 1 billion light-years, is significantly cooler than its surroundings. Standard explanations, like a vast cosmic void, don't fully account for its temperature drop. Some theorists wonder if it's the afterimage of a collision with another universe, a bruise from a long-ago encounter with a parallel bubble of reality in the multiverse. String theory's landscape of infinite universes allows for such rare interactions, where two expanding space-times briefly graze each other, leaving behind a pocket of distorted radiation. The most haunting possibility, though, is that these anomalies aren't anomalies at all, but signs that our understanding of spacetime is fundamentally incomplete. Just as Mercury's wonky orbit revealed flaws in Newtonian gravity, the CMB's quirks might be nudging us toward a deeper theory: quantum gravity, extra dimensions. A universe with an intrinsic preferred frame. Each idea comes with its own set of paradoxes, but the CMB refuses to let us ignore them. It's as if the cosmos left us a cryptic message in its oldest light, and we're still learning how to read it. For now, the axis of evil and its siblings remain unsolved, a cosmic riddle scribbled across the sky. Every new observation, from next-gen telescopes to simulations of alternative cosmologies, brings us closer to cracking it. And somewhere in that ancient light, the universe might be whispering secrets about its birth and what came before. What if every choice you've ever made, from what you ate for breakfast to the job you took, didn't just shape your life, but spun off entirely new universes where the opposite happened? This isn't science fiction, it's the heart of the multiverse theory, a mind-bending framework where time doesn't flow in a single line but branches endlessly like a cosmic tree. At its core is the idea that every quantum event, every decision point, creates a fork in reality, spawning parallel timelines where all possible outcomes play out simultaneously. Picture a library where every book tells the same story but with one altered detail in each. That's the multiverse, an infinite collection of what-ifs given physical form. The roots of this idea stretch back to quantum mechanics' most famous thought experiment, Schrödinger's cat. In the sealed box, the cat is neither alive nor dead, but exists in a superposition, a ghostly blend of both states, until observation collapses the possibility into one outcome. But what if that collapse isn't the end? The many worlds interpretation, proposed by physicist Hugh Everett in the 1950s, argues that the universe doesn't choose. Instead, it splits. One timeline holds a living cat, another a dead one, and both unfold independently, their inhabitants unaware of the other's existence. In this view, reality isn't a single thread but a tapestry of diverging paths, woven by every quantum roll of the dice. This isn't just philosophy. lab experiments with entangled particles consistently show that quantum systems resist being pinned down to a single state until measured. The double-slit experiment, where particles act as both waves and particles until observed, suggests that all possibilities coexist until the moment of measurement. If you extend this logic to the macroscopic world, to people, planets, even time itself, you're left with a cosmos where every possible history and future is real. Missed a train somewhere, a version of you caught it, won the lottery in another universe, you're still checking tickets. The implications are staggering. A multiverse where Napoleon won at Waterloo, where dinosaurs never went extinct, where you never clicked on this video. But how does time fit into this? In a branching multiverse, time isn't a river but a delta, constantly splitting into new channels. Some physicists speculate that these branches might not even run at the same speed. A second in one timeline could stretch into years in another, depending on local gravity or velocity differences. Others suggest that quantum entanglement could link parallel worlds, allowing subtle influences or even information to leak between them. Imagine a déjà vu moment not as a memory glitch, but as a fleeting resonance with another you in a nearby timeline, living the same instant with a hair's breadth variation. The most haunting question isn't whether these alternate realities exist, it's whether we could ever perceive them. If the multiverse is real, it's meticulously hidden, with branching timelines forever out of reach. Yet some theories hint at possible contact points. Quantum tunneling, where particles phase through barriers, might have a multiversal counterpart. Cosmic rays with inexplicable energies could be fallout from collisions between adjacent universes. Even the mysterious dark flow, the unexplained motion of galaxy clusters, has been floated as evidence of gravitational tug from other realities. Critics argue that the multiverse is untestable, a metaphysical escape hatch for physics' unsolved puzzles. But proponents counter that it's the natural extension of quantum mechanics math, a universe so vast it contains all possible versions of itself. Whether prophecy or pipe dream, the idea reshapes how we see time, not as a line, but as an explosion of possibilities where every moment births new worlds. So the next time you hesitate at a crossroads, remember somewhere you didn't, and both versions of you are equally real. Mastering time anomalies could revolutionize humanity's reach across the stars, not by building faster ships, but by bending spacetime itself to our will. Imagine a spacecraft that doesn't fight against the cosmic speed limit of light but sidesteps it entirely, compressing the fabric of reality ahead while stretching it behind. This isn't fantasy, it's the principle behind the Alcubierre warp drive, a theoretical concept rooted in Einstein's equations. Proposed by physicist Miguel Alcubierre in 1994, this warp bubble would allow a ship to ride a wave of distorted spacetime, effectively moving faster than light without locally breaking any physical laws. Passengers inside would experience normal time, while outside observers might see the vessel vanish in one star system and reappear in another, as if hopping through a fold in the cosmos. The implications for interstellar travel are staggering. A warp-capable ship could reach Proxima Centauri in weeks instead of millennia, turning colonization into a practical endeavor rather than a generational gamble. But the hurdles are equally immense. Alcubierre's model requires exotic matter with negative energy, a substance that defies gravity by repelling spacetime instead of attracting it. While quantum mechanics allows for fleeting instances of negative energy like the Casimir effect between ultra-close plates, scaling this up to warp drive levels would demand energy densities comparable to converting Jupiter's entire mass into pure fuel. Some estimates suggest needing the equivalent of 100 times the observable universe's energy to power a single jump, a clear non-starter. Yet recent breakthroughs offer glimmers of hope. NASA Eagleworks lab has experimented with microscopic warp field interferometers, aiming to detect spacetime distortions at quantum scales. Meanwhile, physicists like Dr. Harold Sonny White have proposed refinements to Alcubierre's math, suggesting that shaping the warp bubble into a toroidal ring could reduce energy requirements by orders of magnitude, perhaps down to the mass energy of a small moon. Even that remains far beyond our reach, but the trajectory is clear. We're inching from pure theory toward testable hypotheses. Here's where time dilation could play a crucial supporting role. Even without warp drives, relativistic speeds offer workarounds for human longevity during interstellar trips. A ship accelerating at a steady 1 gravity comfortable for passengers could cross the Milky Way in just 12 years of onboard time, thanks to Einstein's time-stretching effects. Combine this with suspended animation, another area of active research, where cryogenics or metabolic slowdown might pause biological clocks, and multi-generational voyages become survivable. The catch: everyone left on Earth would age tens of thousands of years in the meantime. This asymmetrical aging creates an ethical quandary. Do we send out explorers knowing they'll return to a world that's forgotten them? The darkest twist involves causality. Faster-than-light travel, whether via warp or wormholes, risks shattering the sequence of cause and effect. In certain scenarios, arriving before you left could create paradoxes like the infamous grandfather paradox, where killing your own ancestor erases your existence. Some physicists argue quantum mechanics might enforce self-consistent timelines, preventing contradictions through sheer probability. Others suggest every FTL jump spawns parallel universes, branching reality to absorb the paradox. Either way, mastering time anomalies doesn't just demand engineering prowess. It forces us to confront whether the universe permits or punishes tampering with time's arrow. For now, interstellar colonization remains a dream woven with equations and uncertainties. But the very fact that serious scientists are crunching these numbers, testing these concepts, and debating these implications signals a profound shift. We're no longer fantasizing about slipping the bonds of Earth, we're calculating how to do it. And somewhere in the interplay of warped spacetime, negative energy, and dilated clocks, the future of humanity's journey to the stars is quietly taking shape. Time travel isn't just a scientific challenge, it's an ethical minefield. Imagine stepping into the past and accidentally altering a single event, no matter how small. A misplaced footstep could crush a butterfly, triggering a chain reaction that rewrites history. This isn't just the plot of a sci-fi story. It's the heart of the grandfather paradox, one of the most famous thought experiments in temporal physics. If you traveled back and prevented your grandfather from meeting your grandmother, would you cease to exist? Or would your actions create a splintered timeline where your birth never happens, while the original history remains untouched? The paradox forces us to confront whether time is a fragile thread, easily unraveled, or a self-correcting force that resists tampering. Stephen Hawking famously tested this idea with his tongue-in-cheek time traveler party. In 2009, he hosted an event with a twist: invitations were only sent after the party ended, ensuring only those capable of time travel could attend. The empty room seemed to prove his point. If time travel were possible, we'd already know. But the experiment also highlighted a deeper truth. The universe might enforce cosmic censorship, preventing paradoxes before they occur. Hawking's chronology protection conjecture suggests quantum effects would create catastrophic feedback, like a surge of infinite energy, to stop time loops from forming. It's as if reality has built-in safeguards against tampering with causality. Beyond paradoxes, there's the risk of temporal pollution, unintended ripple effects from even well-meaning interventions. Picture a traveler returning to ancient Rome with modern medical knowledge, curing a plague that once culled millions. On the surface, it's heroic, but what if that plague was a crucial population check, and its absence leads to overpopulation, famine, or unchecked wars? Historians call this the law of unintended consequences, and in a temporal context, it could spiral into catastrophe. The past isn't a static diorama. It's a delicate web of interconnected events where pulling one thread might collapse the entire tapestry. Then there's the question of temporal privilege, who gets to use time manipulation and who suffers its consequences. If time travel or dilation technology existed, it would likely be hoarded by the powerful, creating a new axis of inequality. Imagine corporations exploiting time loops to rehearse stock trades, or militaries revisiting battles until they achieve victory. The ethical chasm widens when you consider cultural erasure rewriting history to favor one group's narrative over another's. Time manipulation could become the ultimate weapon, not just altering events but erasing entire identities from existence. Even seemingly harmless actions could have cosmic repercussions. A traveler leaving behind a modern artifact, a soda can, a smartphone might inadvertently jumpstart technological revolutions centuries early, collapsing the natural trajectory of innovation. Physicists call this the contamination problem, and it's why some theories of time travel require strict isolation protocols, like existing only as intangible observers in the past. But enforcing such rules would be nearly impossible, especially if time travel became democratized. The darkest scenario isn't paradox or pollution, it's predestination paradoxes, where attempts to change the past only cement it. In this model, time isn't just resilient, it's actively conspiring to ensure events unfold as they always have. A traveler trying to stop an assassination might inadvertently cause it, becoming the very trigger they sought to prevent. This isn't just philosophical. Quantum experiments like the delayed choice eraser suggest particles can retroactively change behavior based on future observations, hinting that causality might be more malleable and more sinister than we think. Ultimately, the ethics of time manipulation force us to grapple with humility. The past isn't ours to edit, and the future isn't a script we can rewrite without consequence. Whether through paradoxes, pollution, or privilege, tampering with time risks unraveling the very fabric of reality, not just for us, but for every life that ever was or will be. Hawking's empty party might be less a dismissal of time travel and more a warning. Some doors are meant to stay closed, from black holes warping time into pretzels to quantum particles seemingly telegraphing their future states. We've journeyed through a cosmos where the rules of time aren't just bendable, they're downright chaotic. We've seen astronauts lose minutes in orbit, pulsars stutter like broken metronomes, and cosmic strings that could, in theory, stitch timelines into loops. The Pioneer probes drifted off course as if nudged by invisible hands, while dark matter's gravitational shadows might be hiding pockets where clocks tick at different speeds. And let's not forget the wildest twists, white holes spewing out reality like cosmic fountains, or the spine-tingling possibility that our universe is just one line of code in a vast simulation. Its time glitches nothing more than processing errors in some unfathomable program. Yet for every mystery solved, a dozen more erupt. Why do some temporal anomalies like the cosmic microwave background's eerie axis of evil defy every model we've built? Could quantum entanglement's spooky connections be threads stitching parallel universes together? And if time loops exist, why hasn't a single tourist from the future crashed our history books? The truth is, we're still scratching the surface. Physics humbles us at every turn, revealing a universe far stranger than our boldest fictions. That's the real magic here. Time isn't some rigid scaffold. It's a living, twisting thing full of secrets we've yet to crack. Maybe the answers lie in undiscovered dimensions, or perhaps they're hiding in plain sight, woven into the fabric of everyday reality. One thing's certain, the more we learn, the more the universe laughs and shows us another card up its sleeve. So now it's your turn. Which of these time-bending theories makes your head spin the most? Are you Team Wormhole, convinced cosmic shortcuts await discovery? Or do you think the multiverse's infinite branches hold the key? Drop your favorite theory in the comments, because the next great breakthrough might just start with a conversation. And who knows, maybe somewhere in some twisted corner of space-time, a future version of you is already reading this and grinning.